Okay, so this work is some type of Bulow-Klemperer result for those who know it for multidimensional bidders. And it's a joint work with Michal, Ophir, Inbal, and Matt. Okay, so let's start with the welfare maximization. So this is a standard. We all know this. We want to maximize welfare. We have one item for sale. So we just sort the bidders by value, allocate the item to the one who values it the most, and it pays the second highest price. And it maximizes for every input, it maximizes the welfare. We don't need any assumptions. But if we start talking about revenue, it's a bit more complex. So for a single item, we already talked about it. We need some, for a single bidder, we already talked about it. We need some prior information about the bidder. And we just choose the price that maximizes the expected revenue, which is the price times the probability of sale, when f is the density function of the bidder. And for multiple bidders, we just run second price, but the bidder also has to suppress the reserve price, which is the same P as before. And this is milestone options. And the interesting thing about it is that we require the prior knowledge in order to get something that's optimal. We cannot optimize without the prior knowledge. And a really elegant and similar result of Bulow-Klemperer says that instead of running the optimal mechanism, if we have some population, we can just recruit another bidder from the same population, from the distribution, and run the second price auction, which is prior independent, which means it doesn't depend on the details of the distribution. So it's much, we don't need to do market research. So there's a trade-off. Either we can do some market research and get the optimal thing, or we can just advertise, get another bidder, and we're fine. So let me talk a bit about the proof shortly. Okay, first of all, we assume regularity. This theorem and all of my talk assumes regularity. You have to have regularity for this kind of results. And intuitively, I won't explain it in details, but it means that the distribution is not too heavy-tailed. So the proof is in 3 steps. The first step is to upper bound optimal revenue. The second step is to find some auction with more bidders that covers the upper bound we found in step 1. And the third bidder is just showing that the second price auction beats the auction we found in step 2. And chaining these together gives us that the second price auction with more bidders covers the optimal revenue. And what are the 3 steps? So step 1, we already talked about it. It's milestone auction. We just, in order to get the optimal thing, we just run a second price with reserve. So step 2, imagine we have another bidder from the same distribution. Then what can we do? We can just run on n bidders on the milestone auction. And if we don't sell, we just give the extra bidder for free the item. So it's clear that it makes as much revenue as milestone because we specifically run milestone auction. And step 3 is due to a simple observation that is a result of milestone work, is that the second price auction is the optimal auction out of all auctions that always allocate the item. Because we want to maximize the virtual welfare, and the virtual welfare corresponds to the highest value. So this is the whole proof. And we want to extend it beyond a single item. So instead of one item, we have several items. Each item has some prior distribution, which is different. And each bidder is symmetric with the distribution. Each bidder has the same product distribution over items, which means that the values for each item for each bidder are drawn independently. And most of the time, we assume the bidders are additive. It means that the value of a bundle is the sum of the values of the items. Okay. So in this setting, as explained in previous talks, it's really complicated. We don't fully understand the optimal mechanism yet. It's not like in the single setting where milestone gave us a nice characterization. Sometimes we need to use randomization. It's intractable to compute the optimal auction, and only recently some approximately optimal and simple mechanism were devised for this setting. So let me stress that if in the single item setting we have some trade-off between whether to do market research or to advertise. Here, even if we have the priors, even if I give you the priors, you can't really optimize the revenue. So it's even more important in this setting. So let's state our results. So we use a new definition, a new notion which we call competition complexity for the simplicity of representation, which means the following. I fix some environment, let's say n bidders additive, and I ask what is the number of bidders x that I need to add to the environment, such that running VCG on the original bidders plus the new bidders gets me more revenue than the optimal prior dependent mechanism, which only has n bidders. So let's, for warm-up, let's say what's Bulow-Klemperer in this language. So the competition complexity of a single item auction is only 1, because we need x has to be only 1 in order to surpass the optimal revenue. So this is the standard Bulow-Klemperer. So let's state our results. The first result we have is that if we have n additive bidders drawn for a product distribution over m items, then the competition complexity is at most n plus 2 times n minus 1. This is the first result. We further extend it to bidders that are additive subject to downward close constraints. So they have sets of items which they get the full value for, and these sets are downward closed. So we have some sort of reduction. Let's say we have some bound C on the competition complexity of n additive bidders. Then if we consider additive bidders with identical downward closed constraints over m items, we need addition to the extra C, we need an additional m minus 1 bidders. So this is some sort of reduction. If we improve the bound for additive bidders, we improve the bound for additive bidders subject to downward closed constraint. And we further extend the result to settings where the bidders might be additive subject to non-identical downward closed constraint. They could be randomly drawn from some distribution, let's say. So this is kind of nice because we can say something about a market with some bidders are additive, some bidders are unit demand, some want most 5 items or whatever. And we can still bound the competition complexity, although the bidders are not symmetric in the feasibility constraint. But let me, yes?
So they're IID from item distributions, but how the values combine from the item distributions may be different?
Exactly. So the value distributions are still symmetric. We have to have this. But the feasibility constraint might be different. And the only constraint we have is that all the singletons are feasible. All the singleton items are feasible. Otherwise, so Aviad already saw that. OK, so let me summarize the results. So we have a column of the upper bounds, which just mentioned. For additive, the competition complexity is we need to add at most n plus 2 m minus 1 bidders in order for VCG to beat the optimal mechanism. If we have identical downward closed constraints, we need an extra m minus 1 bidders. If we allow different feasibility constraints, we add another m minus 1 bidders. And if we have a metric constraint, we have some refined bounds that depends on some parameter which I won't explain what it is. And we have some lower bounds which are not the most up-to-date lower bounds are not due to our work. It's due to one ongoing work by Feldman, Friedland, Rubinstein, and one previous work for unit demand bidders by Rafgar and Talgam Cohen and Yan. So the lower bounds are n times log m over n. So this means that we can't read for large m, we can't get rid of the dependence on n. And if n is approximately m, we still can't get rid of the dependence on m. So we can't really get rid of these dependencies. Okay. And let's talk about some related work. So the most related work, as far as we know, is the work by Rafgar and Talgam Cohen and Yan, who said that if we take a market with unit demand bidders and add m extra bidders and run VCG, then we get more revenue than the optimal deterministic district mechanism. So the number of bidders that they need to add is less, but they compete against a different animal. They competed against the deterministic auction whereas the optimal auction, there are cases where it's randomized. And they look at this mechanism, and we look at BIC mechanism. So we compete against a more general optimal auction. And it's also, the work also resembles the notion of prior-independent mechanisms in which you don't have the prior, but you still want to have some approximately optimal mechanism without adding bidders. So there were some works, one by Devano, Hartline, Carlin, Nguyen for unit demand bidders, who gave an 8 approximation, I think. And Rafgar and Tangram, Cohen, and Yan gave some nice trade-offs for unit demand bidders. And recently, Goldner and Carlin showed the prior independent mechanism for additive bidders. And it's also has some similar flavor to the notion of sample complexity, which means how many samples from the prior do we need without knowing the prior in order to learn the parameters that allow us to approximate the optimal mechanism. And the difference, again, is that we use the samples as bidders. We can actually allocate them and charge them. And we don't approximate. We get above the benchmark. Okay. So let's start with, let's prove something really simple. Let's prove the competition complexity of a single additive bidders. And we use the same 3 steps of the Bulow-Klemperer proof. The first is devise some upper bound on the revenue. The second is come up with an auction that covers the upper bound. And the third is showing that VCG beats the auction we devised at step 2. And we even look at a simple case in which the items are not identical, but the values, the bidder's value for the items is identically drawn from the same distribution. Okay, so the first step, upper bound the optimal revenue. As we discussed throughout the day, the optimal revenue is not well understood. It's a really weird creature. But recently, Kai, Devenu, and Weinberg gave a real nice framework to give upper bounds to the optimal revenue. So without going into too much detail, what they do is they formulate revenue maximization as an LP, take the Lagrangian dual, and then some smart instantiations give us meaningful upper bounds. So for instance, in their work, they gave the following upper bound on the optimal revenue. Let's say that the items are IAD drawn. So let's go over this upper bound. So the optimal revenue is upper bounded by expectation over the values of, OK, so we have here phi, which is the virtual value function, as we know it, but only the positive portion. And we have, we sum over all the items. And for each item, we have 2 options. Either the item is the most attractive item for the bidder, the one with the highest value. In this case, we take the item's virtual value. Or there's some other item which is more attractive to the agent, and then we just take the value. So we truncate the favorite item at the virtual value, basically. This is what this upper bound gives us. And now for step 2, we have the upper bound. So we want to find an auction that gets this revenue. And here we use the fact that VCG is actually, for additive bidder, is actually separable across items. It succumbs to running second price for each item separately. So instead of finding an auction that covers the revenue, we find a single parameter auction that only covers item J's contribution to the revenue. Because afterwards, we use only the second price on item J to cover this auction. So what's the J's contribution? We get rid of the sum and take only J here. And here's the new objective. We need to find a single parameter auction for item J that covers the bound for item J, the contribution of item J. And the mechanism that we come up with is that we add m-1 bidders. We now have, instead of 1 bidder, we have m bidders. And there's a single item J for sale. And we run a second price auction with lazy reserves, which means that the bidder, OK, we look at the highest bidder. And if he wins, only if his value is higher than the reserve. This is the second price auction with reserves. And we have different reserves. We have reserve, the minimal value in which the virtual value is non-negative for agent J. And for all item J, we have a reserve of 0. Okay, so let's look at the auction and let's split into cases. So for the first case is that agent J has the highest value out of all agents. In this case, he wins only if he passes the reserve, which means his virtual value is non-negative. And we use the equivalence between the revenue of an agent and the expected virtual value to say that in the case that the agent J is the highest agent, we get this term of the upper bound. We get the positive portion of the virtual value. The second case is that there is some bidder with a higher value than agent J. And in this case, we use the fact that the second price is larger or equal to agent J because is not the highest bidder, is at most the second highest bidder. So in this case, we know that the winner paid at least agent J's value because it's a lower bound on the second price. So we covered the benchmark for item J with this auction. And now it suffices to show that VCG beats the auction, which means that second prize on item J beats item J, the mechanism we devised for item J. So here we have three inequalities. First, AJ is just the VCG with lazy reserves, which gets less than the optimal mechanism. And now we can use a classic Bulow-Klemperer to say that second price with an extra bidder beats Milestone's mechanism with m bidders, and we get that if we run VCG with m plus 1 bidder, if we change all the inequalities, we get more revenue than the single bidder's optimal revenue. So this gives us a competition complexity of at most m for a single additive bidder with valuations ID drawn. So how do we go beyond ID items? If the items are drawn from different distribution, then the benchmark is a bit different. We have here the virtual value of item J, which depends on the distribution of item J. And we have the priors are different for all items. And if we try to use the same proof technique, it fails because we cannot couple the event that agent J is the agent with the highest value for item J with the event that item J is the most attractive item because the agents are drawn IID from distribution of item J, while the items are drawn from different distribution. So this benchmark actually doesn't help us in proving the upper bound, but luckily we can use the duality framework to prove a different benchmark, which instead of taking the virtual value when the value is the highest, we take the virtual value when the value is the rarest value, the highest quantile. So we take the virtual value of the rarest item and the value of all other items. And now we can couple the event that agent J is the highest agent, is the rarest agent in a sense, and the event that item J is the rarest item. So for those of you that haven't seen it, you need to think about it for a couple of minutes, but it all works out if you take this benchmark instead of the previous benchmark. And this gives us that the computation complexity of a single additive bidder is bounded by m. And going beyond a single bidder, we have a couple of obstacles. The first is the benchmark is much more involved. It has several bidders and has some dependencies between bidders. And therefore, we need to devise a much more complex single parameter auction, and we also need to have different coupling because we have much more events. I won't get into details. And now the question, how do we extend the result beyond additive bidders? So we just, we've shown it for a single bidder, but let's say we have some bound on the competition complexity of n additive bidders, which is C, which means that the optimal revenue with n additive bidders is bounded by the revenue of this VCG with n plus C additive bidders. So we changed some more inequality. On the left side, we can say that the revenue of n additive bidders is larger than n additive bidders subject to downward close constraint. And intuitively, the reason for this is you can take every optimal mechanism that is feasible for the downward close bidders and run it for the additive bidders. It's still feasible. So we have only a larger outcome space of auctions, so we can get more revenue. And if we prove the right inequality, which says that if we add, if we compare VCG with a certain amount of additive bidders to VCG with the same amount plus n-1 additive subject to constrained bidders, then we get more revenue. Then if we prove this inequality, we can show that the optimal revenue with n downward closed bidders is less than the optimal revenue than the revenue of VCG with n plus c plus n-1 downward closed constraints, which gives us an upper bound of c plus n-1 on the competition complexity of additive subject to downward closed constraint. So this is so all the other steps are straightforward, and this is the main technical thing we need to show, and I won't have time to show it. It requires some combinatorial arguments, but let's not dwell in it right now. And we have some open questions also. The first is give tighter bounds and trade-offs. We have lower bounds and upper bounds that are not matching. We also might want to consider more complex valuation than additive subject to downward closed constraint, like sub-additive, sub-modular, or XOS. And we can also ask the question, why do we insist on running VCG as a prior independent auction? There are other prior independent auctions. Maybe they give us better competition complexity bounds. And some of these questions are now investigated by Feldman, Friedler, and Robinstein. So thank you.